All right. Hello, everyone. Welcome. We are going to, in this lecture, discuss solutions. Thus far, we've been talking about solutions, right? We have talked about the nature of a solution, its definition, how we describe solutions according to their components, namely their solutes and their solvents, and also how those solutes and solvents could interact in order to allow dissolution to happen. So that's all great. Like now we have this like beautiful theoretical understanding of solutions. However, as chemists, we do not live in purely just a theoretical world, right? We do things in the lab. So we're going to continue our conversation about solutions, but shift our framework a little bit to describe what chemists care about solutions, or maybe even it's better to say how chemists describe solutions. Like, what's the utility in knowing all this stuff about solutions? How is it that we can communicate any information about a solution to one another as scientists? So our main methods of doing that we know from Gen Chem 1 is we can use some extensive properties of our solution, like concentration, molarity, or we can use some other type of solution properties like density. And these are the solution characteristics that I really want to describe in detail today, because if we are comfortable with how to use molarity and density, that's going to really help us when we start talking about new concentration units. So let's jump in. All right, concentration, molarity. So let's remind ourselves about what solution concentration is in general, and then we will give ourselves a refresher on the mathematical definition of one way of expressing concentration, which is molarity. So recall, the concentration of a solution describes some proportion of solute quantity the part in our fraction to either solution or solvent quantity. What we might refer to as the whole. And that is really particularly true when we are talking about the entire solution. That's when we mean when we say the whole. So concentration describes like how much solute there is in solution. So how much solute per solution. That's what makes it a proportion. Now, from Gen Chem 1, the concentration unit that you are probably most familiar with is the concept of molarity, which is abbreviated capital M. And molarity, I think, is one of the more useful concentration units to chemists because it relates to a quantity of particles via the mole, right? It's in the language here of the name. We can hear mole in that root molarity to some amount of solution volume, right? So it allows us to determine the amount of solute in moles per liter of solution. In other words, molarity, capital M, is moles solute per liters of solution in total. So this is our part, and this is our whole. Molarity. So why is molarity useful to us? Again, concentration allows us to understand like how much solute is present. So like we know, oh, if I had a liter of solution in front of me, if I knew its molarity, I could tell you how many moles were in that liter of solution. But also molarity, because it's one of these things that involves like the per unit, right? It is a proportion. So if you have to say per in the unit, that means we are looking at some kind of proportion of two variables or ratio or quotient of two variables. Those all mean the same thing. And anytime you're looking at a compound unit like that that has per in the language, we are looking at a conversion factor. So we can use molarity to convert between the two extensive properties, moles and liters. So we've got moles of solute and liters of solution. Molarity allows us to do that conversion. So let's practice that conversion, right? I think we can do things like find moles, divide by liters. So let's maybe practice finding some molarity, and then we will try to figure out how that molarity could be used as a conversion factor. So practice determining molarity. So let's look at this problem here. What am I saying? What is the molarity? So what is the molarity of a sucrose solution prepared by dissolving 3.462 grams of sucrose in 500 milliliters of water? How might we get started? So when reading problems like this, it's always a really good idea to just kind of identify the goal, right? Like, what is the problem asking me to do? So right off the bat, my goal, I'm going to identify by finding this language, what is. You'll also find language like determine or solve for. So here, our goal is to find the molarity, capital M, and we can now start pulling some threads of information out of this problem to help us achieve that goal. So what do we know about this solution? So this solution is a solution of sucrose dissolved in water. So if we try to identify what the solute is, since we're talking about an aqueous solution here, we can think about that as being the thing that was dissolved. So the sucrose solution prepared by dissolving. So the thing that was dissolved was the sucrose. And I know that the sucrose has a mass of 3.462 grams. So that was in the problem. Again, just kind of fishing for information. So sucrose solution, I know that the sucrose is the solute here, and I also know how much of it I have. I also have in this problem some other information about sucrose. I know the molar mass, which tells us how much 1 mole of sucrose would weigh in grams. So this says that if I were to have in my hand or weighed out in the lab 342.23 grams of sucrose, that would contain exactly 1 mole, or 6.022 times 10 to the 23 molecules of sucrose. So molar mass. Going back to our goal, molarity, right? This is moles solute over liters solution. So if we're looking at moles solute, I have information here that I think will allow me to solve for that, right? I know a mass, and then I was given the conversion factor that relates mass and moles. So I could use these values to solve for moles. Now I need to identify the volume of solution in liters. So going back to the problem, molarity of a sucrose solution prepared by dissolving 3.462 grams of sucrose in 500 mils of water. Now, sometimes when talking about solutions, we have to make some assumptions. So here we know that the solvent, right, the thing that is dissolving something else, is water. And we know that the volume of water is 500.00 milliliters. And if we're looking for molarity, we need to figure out what the volume of solution in total is. So where does this idea of an assumption being made come into play? Since we were not told anything else about the total solution volume in this problem, or anything else about the total solution in general, right? We were just given information about the solute and the solvent. We need to simplify some things for ourselves. So let's think about like if you were to go into the lab and you were to get a volumetric flask, right? Awful drawing of a volumetric flask, but you get it. You would probably weigh out your solid sucrose, and then you would have your 500 milliliter line. And that is what you would add water to, swirling in between to ensure that you've had now dissolved all of your solid sucrose in that total water volume. So the assumption that we're going to make here, and it won't always be this case, but in this problem, since we don't have an option otherwise, like we don't know information about the total solution, we're going to have to assume that the volume of water that we were dissolved in is equal to the total volume of solution. This is a pretty common assumption that you can make, but it's not one that we want to get in the habit of making all the time. So let's go here. We're going to say this is also equal to 500.00 milliliters of solution. So then let's try to get our moles of solutes, aka our moles of sucrose. So I have a measured value. That's where you start. 3.462 grams of sucrose. I'm trying to cancel the gram unit and be left with the mole unit. So I need to put my number, right? This tells us grams per 1 mole. So the number 342.23 goes in my numerator or my denominator, excuse me, per 1 mole. If you don't like this visual method, this is the exact same thing as taking 3.462 grams and dividing by 342.23 grams per mole. Grams over grams, that leaves us with 1 over 1 over mole. So 1 over a fraction is the reciprocal of that fraction. So this will put us in the mole unit. So let's figure out what that is. I should probably have known this already, but let's do it together. So we're pulling out our phones. We've got 3.462 grams divided by 342.23. Seems like, 34 over 34-ish should be around like a point something involving a 1 or 10. And when I do this, I got 0.010116 molar. And this is just kind of like my raw results. And now I need to do, that's not molar, that is moles. There we go, moles. And I'm going to carry all of my digits here. I'm not going to round to sig figs yet because I want to retain this number in my calculation. I don't want to round preemptively. I don't want to include any like systematic rounding error. Okay. We have figured out our moles of solute. So now we need our volume of solution in liters. And we had already made the assumption that the volume of water that was given is equivalent to the volume of solution. So I have 500 milliliters of H2O, which we're assuming is equal to 500 milliliters total of solution. And we need to figure out what this is in liters. So we can do our little conversion factor. And I always like to think about this in terms of positive exponents. So I will never have like a 10 to the negative or anything like that. I always ask myself in one of the big units. So here we're trying to figure out in 1 liter, our desire unit, how many little milliliters are there? There are 1,000. So I'm going to divide by 1,000. That's what this is saying, 500.00 mils over 1,000 liters. Nope, over 1/1000th. What am I doing here? Over, yeah, 1,000 milliliters per liter. Okay. Now, moving our decimal. Beware sig figs, right? We cannot drop those trailing zeros. Those matter. So this is going to be 0.50000 liters of solution. So now that I have my moles, 0.010116 moles, I could divide by my 0.512340 liters. So taking our results, dividing by 0.5. Okay, I'm going to show an unrounded value first. So we get 0.02023201 molar. And now let's look at our sig figs. So our sig figs are always determined by our least precise number. In the case of multiplication and division, which is what we did here to find molarity, right? We divided moles by liters. That is going to mean we have to have the same total number of sig figs in our result as we do in our least precise number. So let's go look at our measured values. The measured values that we have are the mass of sucrose. So that's 1, 2, 3, 4 significant figures. And then we also have this measurement of the volume of water, 1, 2, 3, 4, 5 significant figures. So we need to ensure that we have 4 sig figs. We are limited by the sig figs of our mass. So this leading zero doesn't count. 1, 2, 3, 4. Rounding would not round me up. So then this is equal to 0.02023 molar. And this is the concentration of my solution in molarity. So as long as you can get moles of solute and a way of determining the volume of solvent in liters, you can always find the molarity of solution. So in our next video, we looked at how to actually calculate molarity, how to determine the concentration of a solution. And coming up, we're going to get some practice in how we can then utilize utilize molarity as a conversion factor, much in the same way that we utilized in this example here, molar mass as a conversion factor to go between mass and moles. Just molarity allows us to go between moles and liters. So see you in our next video.